Hello and welcome back to Honors Topics in Physics. So today I want to cover a couple things, the difference between mass and weight, and also how to do the free body diagram when an object is on a sloped surface. So first, the difference between mass and weight. Well, first off, what is matter? Because matter and mass are interconnected. So are mass and volume. And all that stuff is mixed together. But what is matter? Matter is basically the stuff around you. It's anything that has mass and has volume. So that is what matter is. Is everything around you matter? Pretty much. Anything that you can see, feel, or touch. A car is matter. It's made up of atoms. Basically, anything that's made up of atoms is matter. Is a thought matter? The thought you had about sleeping in instead of watching this video? No, the thought doesn't consist of atoms. What about the Earth? Is the Earth matter? Yes, the Earth is definitely full of matter. What about a feeling? No, a feeling would not be matter. That is just a perception. What about water? Liquids matter. Yes, water would be matter. It's made of atoms. What about air? A gas. Would that be matter? Sure it is. The air in our classroom has a mass of about 900, or has a weight, of about 900 pounds. So the air definitely has weight and mass and volume. What about a light bulb? Is the light bulb matter? Sure it is. What about the light it produces? Is that matter? That's kind of a sticky question, but we're going to just leave that one with a question mark, because technically it doesn't have rest mass, but it has momentum, which is, I don't know, it's goofy. Okay, what is volume? Okay, we said that this would be connected. Volume is the size of an object. It's how much space an object takes up. It's the bigness or smallness of an object. Mass, okay, indicates how much matter there is in an object. Basically, the number of atoms and that kind of thing related. How many atoms are in an object? Of course, there's more to it than just that. But if you're on the Earth, the more mass an object has, the more it weighs. But that's just if we're on Earth. Okay. And also, the other thing about mass is the more mass an object has, the more inertia it has. Meaning, the harder it is to get moving, or the harder it is to stop once it is moving. Okay. Weight, again, is related to mass, but weight is the force of gravity on an object. And so if we were to go into space where there's no gravity, you wouldn't have any weight. Okay, but would there be any less of you? Did you lose any atoms? Did you lose any matter just because you went into space? No. Okay. So weight changes depending on where you're at, because it's the pull of a planet or some other object on you. Okay, and the pull depends on how close you are to that object, whereas your mass just depends on the atoms that you have, and that just depends on if you're gaining or losing weight. Okay, so weight depends on location. Mass does not. Okay. If you think of an example of inertia or an object having mass, if you were to kick an empty can as hard as you can, okay, it wouldn't hurt too bad. You would just fling it off. If you were to fill that can with sand, give it a little bit more mass, it might you probably would notice it on the tips of your toes, because it might hurt a little bit. If you were to fill that same can full of liquid lead and let it cool, and then kick that same can, you would definitely notice that can resisted accelerating more, because it's got more inertia, it's got more mass, and your toes would hurt. So the more mass an object has, the more inertia it has, the harder it is to get going or to stop going once it is moving. If you were to take a big old dump truck into outer space, this would be a very expensive experiment, because it costs a lot to ship things into outer space, depending on their weight, and this would be a lot of weight to get off the planet. So you've got a big dump truck in outer space, and you grab it by the door handle, okay, and you want to shake this thing up and down. Well, first off, okay, how much weight does it have in outer space? Where would you be so that you might get crushed by the weight of the dump truck? Well, there's nowhere you could be that you'd get crushed because there's no weight. There's really, if it's truly in outer space, there's no planet pulling on it strong enough for it to have any real weight. But it still would have mass. Okay, it still has atoms. It still has inertia. Because that doesn't depend on where you're at. That's universal. So if you were to grab this thing by the door handle and try to shake this dump truck up and down, you would see that the dump truck itself would be barely moving, but you'd be the one that was moving up and down because you've got less inertia than the dump truck. Okay. Mass and weight are even measured in different units. Mass is measured in grams, kilograms, or in the English system, slugs. Weight is measured in newtons in the metric system, or pounds in the English system. So just to kind of summarize everything that we went through, mass depends on how much matter there is in an object. Okay, it's how much inertia an object has. It does not depend on your location, and it's measured in kilograms in the metric system, okay, or grams. Weight, okay, is the force of gravity on an object by some planet or some other object. Okay, it depends on your location. Okay, your weight will change if you go to the moon. Okay, but your mass will not. And it's measured in units of newtons in the English system. Okay. To calculate the weight of an object, it's really easy. There's a simple formula. The force of gravity, or weight of an object, is equal to the mass of the object in kilograms times the acceleration due to gravity at that location, which we're typically on the surface of the Earth. So that'll be 9.8 for us. Okay. So Fg, this is one you want to write down and know. F sub g equals m times g, where on the planet of Earth, okay, g is equal to 9.8 meters per second squared. Okay. So the weight of a 1 kilogram object, if I put 1 kilogram here, okay, and then we have 9.8 newtons here, okay, that's equal to 1 times 9.8, which is 9.8. So roughly 10, or 9.8 or 10 kilogram meter per second squared. And there's a nickname for that. Instead of running around calling the weight of an object in kilogram meter per second squared, we call it a newton. Okay, so you don't need to know what a newton stands for, but just realize that there is this actually stands for basic units that we've already talked about. Okay, so an object weighs 250 newtons on Earth, which it's so our equation is F sub g equals m times g. Okay. So what is the 250? What is the 250? Is that our F sub g, our m, or our g? Okay, that's our weight. That's measured in newtons. So that is 250, right, equals, okay, m, which is what we're looking for. Okay. And we're going to use 9.8 because we're on planet Earth. And so take 250 and divide it by 9.8. And you get 25.5, and m equal 25.5. And do you know what the unit on that would be? What do we measure mass in the metric system? Kilograms. Okay. All right. Okay. Let's skip that. Let's skip that. Let's skip that. Okay. Okay. So let's say we've got a window washer here, and the window washer can rig up their stand, what they're standing on or sitting on, to a rope and attach it to the building one of two different ways. They can just run the rope over the pulley and attach it to the building itself, okay? Or they could run the rope over the pulley and then back to the window washing cart stand, chassis thing, whatever it is. And the question is, does the rope have to be the same strength in both of these scenarios? Okay. So the mass and the seat of the person have a mass of 900 or 100 kilograms or 9,800 newtons. But let's not even worry about the numbers. Let's just look at a free body diagram for each. So if we look at the one on the left, we draw a free body diagram for that person on the left. We've got the force of gravity down, okay, and then what's they're assuming they're in equilibrium. They're not accelerating. What is canceling out the force of gravity? It's got to be an upward force, and that would be the force of tension by the rope. Okay, and if everything is balanced, okay, we draw hash marks, and everything cancels out. So if this is, let's say it's 10,000 pounds, let's round gravity to 10, and say 1,000 pounds. Okay, if there's 1,000 newtons of force down, the force of tension has got to be 1,000 newtons of force up. Okay, so that rope has got to withstand 1,000 newtons. Okay. If we look over at this scenario, we've got the same force of gravity down. Let's say it's our 1,000 newtons of force down. Okay, but what's different is there are two forces of tension going up. So how strong does each force of tension have to be? What's each force of tension? 500 newtons. So by wrapping the rope around it like this, then the rope only has to be half as strong, which is kind of interesting. You wouldn't think by rigging it so similarly it would make such a big difference, but it does. Okay. The last thing we want to cover is how to draw a force diagram when the object is on a sloped hill. Okay, so what we're given is that we've got a sloped hill, we've got the force of gravity drawn, and the force of gravity is down. What you're going to do is you're going to rotate the page, literally like rotate the page on your desk, so that the slope is now flat. Okay? The slope is now flat. Okay? And there's no object shown, but there's a box or something on the hill, and the box is stationary. So what we've got is we've got the force of gravity, we've got the normal force, and we've got the force of friction. Now this isn't how I necessarily want you to do it on this, but just kind of drawing the free body diagram for my box on a hill. So this is a grassy hill. So we've got my normal force that's off into the diagonal to the right. And we've got the force of friction. Oops, that's friction, not gravity. And that's up and to the left. Okay, now the problem with doing it like this is that I've got two diagonal vectors. Okay, and remember how it's kind of nice if we could break these apart into their components and show things cancel. Well, it gets a little bit messy if we've got two diagonals, because then I've got to have these components adding together, and it just is more work than need be. So what we're going to do is we're going to consider the positive x-axis to be down the hill, okay, and we're going to have the positive y-axis perpendicular to the hill in the direction of the force, the normal force. Okay, so I'm going to do this just freehand because I can't really do it with a ruler, but you would do this with a ruler. What we want to do is we want to break this gravity into components that are perpendicular and parallel to the hill. Basically what this involves is you making a triangle like so, okay, where the right angle of the triangle is opposite the force of gravity. Okay, so I draw a right angle here, but it's get it even a little bit messier. So I've got a force of gravity in what we consider the x direction, because we said x is down the hill. Okay, and we've got a force of gravity in the y direction, okay, which we said is perpendicular to the hill. Okay, so if I were to draw this on this picture, it would look oh no, now it zoomed in. Is it going to erase? Yes, it erased. Okay. So what we're going to do is create a free body diagram for a box or some object that's on a hill. So this dashed line represents the hill, and then this force of gravity represents the weight vector. So if we were to draw, and my object is stationary, so the sum of my forces equals 0. So all of my forces cancel. So force is acting on the crate that's on this imaginary hill. We've got force of gravity down. Okay, we've got a normal force. Okay, up and to the right, perpendicular to the hill. And we would have a force of friction that's preventing it from sliding down the hill. So this would be our force of friction. Okay, so these would be our three forces. And as it zooms in, oh my gosh, it's really zooming in. Zoom in for effect. So those would be our three forces that are acting on the crate. Now, we normally like to, if the forces are balanced, we like to use hash marks and show that forces are equal. But I've got two diagonals, which means I'd have a total of 5 vectors, because I'd have 2 for this one, two component vectors for this one, 2 component vectors for this one, and then the force of gravity. So and then I'd be talking about forces having to add up and cancel out and things like that. But there's a trick that we can do. If we consider the x-axis to be down the slope of the hill, and we consider the y-axis to be perpendicular to the hill, that's in the same direction of the normal force, we can rotate the page. So now, okay, my x-axis is directly to the right, and my y-axis is directly upwards. Okay. So when we do this, what we're going to do is we're going to draw the force of gravity at an angle. Okay, and we're going to break it up into its components. Even though it's technically straight down, by rotating the page, we make it at a diagonal. And if you're not following why I'm doing what I'm doing, just hold up. There's a reason to my reasoning here. So what we're going to do is we're going to draw a force component vector straight down. Okay, and then we're going to draw a component vector straight over. And what I've done is I've made the force of gravity the hypotenuse of my triangle. So here I've got, and my right angle for this is directly opposite the force of gravity. So so now when I draw my force of my normal force, which is up, and I'm freehanding this, so you guys should use a ruler. Okay, so this is my normal force. Okay. My normal force cancels out with this force of gravity that's in the y direction according to my rotated page. Okay, so gravity cancels out with the y component cancels out with this normal force. Okay, and then my force of gravity is going to be, my frictional force is going to be up the slope, and so that's my force of friction. Okay, and that's going to cancel out, so we'll use double hash marks to show that it's different but than the first one, but it's the same as the quote-unquote x component. So this is in my x component of gravity. So so by doing this, I can show that gravity cancels out with these two components in a much simpler way than rather than having a total of 5 vectors. We just have a total of 4, and they cancel out rather easily. Okay, and that is it. So that's what I want you to do on the next worksheet, which is 4-4 gravity and page tilting. So practice your hand at these. Remember to tilt the page and draw gravity at an angle and the other forces up and down or left and right. Okay.